Hello YouTube, welcome back to another math video. I know it's been a good while since I had my last video, but I've been really busy with school. But since today is Pi Day, I thought, well, I can't let this day go by without making a fun math video. And so that's what we're doing today. We're looking at the Basel problem, which the Basel boy, being Euler, solved in 1734. And the Basel problem is the sum, the infinite sum from n equals 1 to infinity of 1 over n squared. And that turns out to be pi squared over 6, which is roughly 1.645. So how does the pi get in there? How can we solve this? And there are really, with anything in math, there are an innumerable number of solutions. Probably a definite number, but there's so many different ways of thinking about this and looking at this. But for today, and I will be looking at least two ways. But for today, let's just take a look at Euler's original solution, which is much more heuristic. So it's based on observations and comparisons with similar functions, and saying, well, if these properties hold true for these similar but definite functions, then we can then extend them to interminable functions, as you'll be seeing, because we're dealing with this infinite sum. So, without further ado, let's get going. So, first off, I think to start, let's just take a look at the function f of x equals, x squared minus 4. Well, we know that this is simply the quantity of x minus 2 times x plus 2, right? The sum of squares. So x squared plus 2x minus 2x minus 4. We can agree that's just basic factorization. Okay, and then if we also had the function f of x, say x minus x squared, we could say x, which is really x plus 0, times 1 minus x. Okay, and that's again just factoring out an x, which is really an x plus 0. So you may be asking yourself, okay, well, why am I starting here? Well, these are polynomials. These are all continuously defined on their domain. It's just we have x squared minus 4, x minus x squared. So they all have a coefficient and then some kind of exponent, and there's no kind of weird denominators or square roots or any kind of weird stuff. It's just a plain polynomial. Many terms, right? And what we've done is we've taken these polynomials and we've broken them down, we've factored them, right? And so what you might recall, well, by factoring them, these are the x-intercepts. We've expressed this function in terms of their x-intercepts. And this idea of being able to do this, sort of taking a function and breaking it down into its zeros, right? This is when x is 0, when x equals 2, the function goes to 0, when x equals negative 2, x goes to 0. So it's a parabola, like a bowl hitting negative 2 and 2. So, okay. Well, what if we instead take a look at a different function? So if we've established that we can break up a function into its linear factors, what about sine of x? What about sine? And you might be saying, well, sine, that's not my typical polynomial, right? Well, in theory, this idea should hold true. So if we look at a graph of sine, right, it's going to look like this. right? More or less. So yeah, this is sine. And okay, so the question is, can we take what we just learned about polynomials in terms of taking your function and breaking it up into its linear factors? Can we apply that to a function like sine? And what Euler showed very heuristically is yes. But that won't be actually proven until the Weierstrass theorem, which comes about later in the 1800s. That's not really important for what we're doing today. So if we can say, okay, well, we have that idea of breaking the function down into linear factors. So why don't we just let's start running that. We know sine has a 0 at x. We know it's going to, yeah, so it's every pi, we know that we'll have zeros at every k, or k, every k pi, rather. Every k pi, where k is a subset of real numbers. So for every integer k, positive, negative, times pi, we will have a 0. So for example, this is 0, 0 times pi is 0. This would be pi, 2 pi, etc. And then this obviously being negative pi, negative 2 pi. So why don't we start writing some of these guys out? So we can have, 1 minus x over pi, and then that's this one, and then 1 minus x over pi, so that would become 1 plus x over pi. And then we can go up to 2 pi, so we have 1 minus x over 2 pi, 1 plus x, because remember it's a minus, over 2 pi, and essentially going on infinitely. Okay, well, if we clean this up a little bit, we can say, okay, it's still our x. If we combine these guys, we have 1 minus x squared over pi squared. Combine these guys, 1 minus x squared over 2 pi squared. So that's a squared. And then if we wanted to keep going, we'd have 1 minus x squared over 3 pi squared. Right, okay. I'm just taking these and combining them a little bit. Okay. So what if we then consider the sine of pi x? So essentially everywhere we see an x here, we're plugging in a pi. So this would become pi x. This becomes simply 1 minus x squared. This becomes simply 1 minus x squared over 2 squared. And this becomes 1 minus x squared over 3 squared. Again, going on infinitely. Okay. Well, what if, okay, so we need to, what if we clean this up a little bit? So we can write this as pi x times 1, because pi x times 1 times 1 times 1 times 1 times 1 is always going to give us pi x. And then if we consider these x squareds, if we're just essentially taking this pi x times all the x squareds and then factoring it out, we'll be left with minus x squared times the quantity of just their coefficients. Let's get rid of this big axis here. And then this too. And then essentially this is just going to keep going you essentially could then say, okay, well, we could then look at, you know, we'd have our plus x fourths, and then you could just keep going with that. You know, you'd have what, you know, 1 over, yeah, like 1 over 1 times 4 plus 1 over 1 times 9 plus, it's a 9, plus 1 over 4 times 9. And then, yeah, this is just going indefinitely. This is going to be, oh shoot, yeah. Well, we don't really care about this term so much. We really just care about these guys. You'll see why in a little bit. Okay, so we've converted these products into sums. It's kind of an interesting idea, but we still need to get an infinite sum. We have sine. How can we get an infinite sum somehow from sine? The question is, how can we express sine differently? Well, we can use a Taylor series approximation of sine, right? Do this graph. So the Taylor series approximation of the sine of x is the infinite sum from n equals 1 to infinity of -1 to the n x to the 2n plus 1 over 2n plus 1 factorial. This is the Taylor series definition of the sine of x. And voila, we have our infinite sum. But we don't want the sine of x, we want the sine of pi x. So, if we plug in pi for x, and then can just start calculating the first few terms, we're going to get pi x minus pi x cubed over 3 factorial plus pi x to the 5th over 5 factorial, and again, infinite sum. Okay, now this is when the discussion about polynomials again is going to come back to us. So we talked about breaking up a function into its linear factors. And again, that's what we did here with sine. And this idea of expressing a function like that was proven with the Weierstrass linear factorization theorem. But this is just the observation. We're not going into that proof, we're just saying this is our observation, which holds to be true. Okay, the other key thing now for the remainder of this proof is, how do you know if two polynomials are equal? Well, let's say we had a function f of 1, and let's say this was ax to the b. Let's say we had another function, f2, which let's say was, I don't know, cx to the d. So if a equals c and b equals d, then we can say f1 is equal to f2. Sorry, it's getting very messy down there. In other words, if two polynomials have the same coefficient, this multiplicative factor out front, and the same power, the same degree, then they must be equal. Okay, so how can we use this? Well, we have two expressions for sine. sine of pi x and sine of pi x. We know they're the same thing because we've defined it two different ways. We know each definition is valid. So therefore, if we apply what we just said, we know these have to be the same functions. So if we have a term of the same degree, if we have since we have two equations, we have a term of the same degree. The coefficients must equilibrate. They must be equal to each other, and that's going to be very helpful. So if we take a look at this boy, and then this guy, this well, it's really this pi x times this. The pi x distributed to that. X cubed, right? If we distribute that pi x cubed, x cubed. We know these are the same functions. They have the same degree. Therefore, they must have the same coefficient. So, we then can say, okay, we know that negative pi times, now what is this? Well, given a certain I, you might have noticed it is the very thing we were trying to solve for. 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared. That is the infinite sum of the reciprocal of the squares. So, the infinite sum of 1 over n squared is thus equal to negative pi cubed over 3 factorial. Now we just do some simple algebra. We just say, all right, we want to get rid of this negative sign here, and then we want to get rid of this pi, therefore make this guy go away. It's only squared. And now 3 factorial. Factorial, you're simply taking you're going from your number times the n times 1 minus n times 1 minus n, n times 1 minus n factorial. So 3 factorial is just 3 times 2 times 1, which is 6. So 3 factorial becomes 6. And voila. There we have it. Pi squared over 6, the infinite sum of the squares, when n equals 1 to infinity, is nothing more than pi squared over 6. So, pretty cool proof. What do you think? I mean, nothing really too technical. Essentially, some basic ideas about how functions work, observations that rely on more rigorous proof, but they're observations nonetheless. And so from really 2 simple definitions of the sine function, we end up solving for this sum, which is just really cool. And I think the cool thing about this proof is really its simplicity. There's nothing really that too technical in it. And what's also cool is it gives us this interesting connection between series and products, infinite series, right? Because this is an infinite. These are infinite products. We're turning them into essentially infinite series, and so that's kind of hinting at this deeper relationship between products and sums. I think is at the very core of mathematics, and it's a really neat proof. Really fun way. Really fun for its simplicity and its elegance and its beauty. So that was fun. Hope you enjoyed the video, and I will be making a second video going over a more rigorous proof of Euler's of the Basel problem. Again, borrowing some key information from Euler, some key formulas and other identities. But until then, I hope you have a mathtastic Pi day and a mathtastic rest of your day. So take care.